Okay, so welcome back. As I mentioned in chat, I pasted uh, an online version of Euclid's Elements. It's really nice. I believe this is the same one that that I had looked at previously that had nice like movable diagrams and stuff. I have to look at a couple of these. Let's see here. Where are my diagrams? Maybe I was confused, and maybe this isn't quite exactly the one. I believe this is the same version, but I think there's a. Yeah. Anyway, I'll have to look again later. This is fine for what I wanted to cover, but basically, if you click, yeah, okay, no, this is the one. So if you click on any of the individual propositions in any of those loadouts, you'll get the nice diagrams that you can actually click on each of these things to expand them, and they have nice pictures associated with these things. So anyway, you can have a look at that. And there's there's a little blurb at the end of most of them that tell you the logical structure and give you like the dependence of everything. So basically, every proposition that is outlined in a particular book, it tells you which things were used to prove which proposition. So this is actually really, really nice. And that reminds me, I know I've been promising this info dump for like over a week now, but I sat down to to do it and realized that it was taking me a lot longer than I anticipated because there's a ton of stuff to go into it. So anyway, I will get that. It will be it's an ongoing thing, and in fact it might not even be. I'm gonna post it as an announcement, but I may actually put it as a separate document and upload it to Elms too, just because it's easier to see, and I want you all to be able to see it. Maybe I'll start doing that, having a bunch of supplemental things that I upload that makes it a lot easier to kind of organize this stuff. So anyway, at the end of lecture last time, I'd basically been going over the rest of the elements, basically what things were covered. So the last thing I mentioned was Book 10. So Book 10 dealt with these things that in modern parlance would be called field extensions of degree 4 over rationals. So and it asks questions, among other things, it asks questions of like when something like this is actually only has like one layer of square roots. Okay, and there's a reason for this. The reason for this comes later, by the end of the elements, when Euclid is actually shown there's these certain ratios of lengths to the radius of a circumscribing sphere for these figures. A lot of the ratios involve quantities like this, and so that's the reason for this showing up in Book 10. So after Book 10, in Book 11, there's the move to 3D. So this is solid geometry. So the basics of solid geometry. So basic definitions of solid geometry. You might say, well, how did the Greeks do this? Right? How did they deal with doing geometry, not just in the plane, but also in space? Well, they dealt with it in much the same way we do when we're talking about the basics here, right? So you have a notion of a plane, and then objects lying on or off a plane. Here's another example of a diagram showing up in Book 11. So this is from Proposition 3. And if you quickly flip through Book 11, you see all kinds of pictures like this that you might first see in either a Calculus 3 course or maybe a linear algebra course. Okay, and so these things were dealt with in exactly this manner. Now, there's something that I'll mention a bit later, which is some of these diagrams get pretty intense as this progresses. And so already in Book 11, the immediate move to solid geometry, we already have arguments and diagrams becoming more convoluted. They're not too bad here in Book 11. As we'll see later, they become slightly more convoluted. So here's an example of a rectangular-based prism thing, this box. Here's another example. This is from Proposition 25 in Book 11. So all kinds of these nice pictures showing up. And as I said, these are original drawings. It's not like these things were added later. This was original to the elements. So the basics of solid geometry are discussed. So things like cones, pyramids. How would, for instance, how would the Greeks define a cone or a right circular cone? If we're being really picky on the language here, how do they define a cone? Well, they defined a cone as resulting from taking a very familiar figure, right, a right triangle, and rotating it. So treat, say, this leg, this longer leg, as its axis of revolution, and think about generating, right, a solid by revolving this about that axis of revolution, right? You generate a solid of revolution. That solid, in this case, is the right circular cone. Okay. You could talk about cubes, right? Cubes, easy to define. You think of the solid region bounded by 6 identical squares, right? Your D6. Okay. You can discuss the regular polyhedra. Of course, this comes later, but the main purpose in discussing the basics here is to state a fact that is going to be used later to completely classify these regular polyhedra. And this is Prop 21 in Book 11. So if we go to Prop 21 in Book 11, let's read that really quickly. Okay. So, Prop 11. Any solid angle is contained by plane angles less than 4 right angles. Any solid angle is contained by plane angles less than 4 right angles. What does that mean? So think about what that means for a second. So any solid angle, you can think about what solid angle here means, right? So this is the notion of angle in 3 dimensions, right? So any solid angle is contained by plane angles. These are angles in the 2-dimensional sense. So it's contained by plane angles whose sum is less than 4 right angles. So that's whose sum is not included there. Whose sum is less than 4 right angles. i.e. 360 degrees, right? Now, what is the benefit of this? We've already seen this, actually. We spilled the beans on this when we first talked about the regular polyhedra, right? So if we go back to our discussion of the regular polyhedra, and you remember that table that I drew up a table when we were talking about the Pythagorean solids here. Where are we? Now I can't find my table. Here we go. Right. Talking about the Pythagorean solids and these tables, especially here. Figuring out this sum of 1 over P and 1 over Q, right? Which of those would work out? Well, it turns out that restriction and, me being able to show that there's only 5 of them comes from this fact. So the reason why this is shown in Book 11 is because in Book 13, Euclid wants to say everything there is to say about the Platonic solids or the Pythagorean solids. Okay, so Book 12, did I still have room on that? No, I was basically out of room. So Book 12, this is due to Eudoxus, most likely. This was kind of, other than his theory of proportion, this is kind of his crowning achievement. So this is computing the volume, so the volumes of pyramids and cones. So pyramids, cones, and spheres. Okay. Now, of course, this is done with no calculus, obviously. Calculus wasn't invented until the 1600s, so this is done without any help of calculus. And this is a pretty amazing feat. If you want to see what some of these images look like, well, you can have a look. As I said, here's the end of book 11, actually. Some of the images here. This is the beginning of book 12. Okay, so again, look what's going on here. Proposition 2 of book 12. Circles are to one another as the squares on the diameters. Look at the method of proof used, as we mentioned before, right? So circumscribing, or thinking about inscribing a 2 to the n-gon here, right? And of course, Archimedes would finish this entirely to do a bunch of things. So one, Archimedes would show finally the area, the formula for the area of the circle, as well as use this to estimate pi. Okay, so here's examples of computing something about volumes of pyramids. Again, volumes of pyramids, and so on. Okay, so this is pretty impressive stuff. Some of the diagrams and some of the arguments get really torturous because the pictures become very muddled in cases. So here's a couple of examples of dealing with cones and cylinders that have the same base. So all this is the contents of book 12. So as I was mentioning before, as these diagrams are getting worse and worse, to deal with some of these computations, it turns out that if you bring modern algebraic machinery to bear on this, it makes some of the computations really, really easy. So for instance, if you bring like linear algebra into some of these arguments, it makes some of these, if you bring coordinates and linear algebra into the picture, it makes some of these computations extremely easy. Something that you could basically give to a linear algebra student, when they're first learning the material. So it makes some of the computations a lot easier. For this reason, after World War II, there was a push, beginning with French mathematics. There was a push to do away with teaching, Euclid's Elements or Euclid at all. In a sense, teaching geometry this way as a way of building up, logical argument. And their big push was, down with triangles, literally was like their mantra, down with the theory of the triangle, and pushing forward with just linear algebra. So replacing all of compass and straight edge construction and all that stuff with linear algebra. And there's some arguments for that being fine, but it's better for that to be a supplement. And so if you want to actually see a good treatment of that, you can look at my 430 course, which that's the first 2 parts of the course that it does. So that course Math 430 covers 8 chapters of a textbook called The 4 Pillars of Geometry. And basically it's split into 8 chapters, each split into pairs. There's 4 pillars, and each pillar is covered as a pair. The first pillar is Euclidean geometry in the sense of compass and straight edge constructions and Euclid's Elements, that type of stuff. And the second pillar is linear algebra. But there's a reason why the picture's not complete there, and if you do away with the constructions, you miss out on some really, really good geometric insight that comes later. So you can't just throw out Euclid and replace with linear algebra. And I mean, you can't do that at all because you're missing out on a ton of stuff. Anyway, so this was book 12 due to Eudoxus. So book 13 is the culmination of all of this, where Euclid classifies, so classification of the 5 Platonic or Pythagorean solids. So what this means is computation of ratios of side lengths to inscribing sphere radii. Okay, this is where these computations in Book 10 come in handy. And then lastly, the proof that there's only 5 of them, which relies on that fact that I mentioned previously. So the proof that there are only 5 such solids. So this totally nails down the regular polyhedra. Okay. Okay. And so here's the very last statement is a lemma in Euclid's Elements, that the angle of the equilateral and equiangular pentagon is a right angle and a fifth. Okay, so this is measuring. Notice that it is inscribing this pentagon in this circle here, and again computing these ratios. Okay, so as I've said before, this was used as a textbook for about 2,000 years, and it really wasn't until after World War II that these major objections started being used, that, oh, there was a better way to teach this sort of geometry, and that's using modern machinery like linear algebra to get rid of some of these really torturous arguments. But hopefully by the end of the course, and if you look at any of my Math 430 videos, especially the early ones, and I'm actually going to link you to one later to supplement what I'm about to talk about, you'll see that it's not a good idea to toss out this. So Euclid was really on to something here, especially with the way that these ideas were presented and developed is something that is so influential that it's still, literally every single math paper that's published right now is still laid out in the exact same way as the Elements. So anyway, so that's Euclid's Elements. And this is a massively influential book. Before I get on to what happened in Alexandria after Euclid, so what the students in Alexandria, or which were the influential students in Alexandria afterwards, I want to talk about non-Euclidean geometry. Now, I'm not going to give an exhaustive treatment of this because it would take too long to develop everything that I would need to in order to talk about this. As I mentioned previously, we already saw an example of non-Euclidean geometry on the sphere. Okay, but when we talk about non-Euclidean geometry, the reason spherical geometry gets tossed aside is it's a little too weird. It's a little too exotic, right? There's no such thing as parallel lines. 2 points do not really determine a line. If you pick antipodal points on the sphere, there's multiple options for lines between them, right? So it's a little weird compared to what we're used to. So the idea is that if we assume absolute geometry. What is absolute geometry? So absolute geometry is postulates 1 through 4. Okay, so assume postulates 1 through 4. So pretend that we live in a world where all we are taking as assumptions are postulates 1 through 4. This is called absolute geometry. So assuming this, postulate 5 has many alternative. So postulate 5 has many equivalent statements. This is not an exhaustive list of equivalent statements, but here's a few. These statements were arrived at by mathematicians attempting to prove the fifth postulate from the fourth. Now, Euclid included the fifth postulate because he couldn't figure out a way to do this. The reason he couldn't figure out a way to do this was not because he was stupid or lacked the insight. It's because it was impossible. Okay, so it turns out to be impossible. Assuming absolute geometry, that is postulates 1 through 4, you can't prove postulate 5 because it is logically independent from the other 4 axioms. What that means is that there are examples of geometry where the first 4 postulates are true and the 5th one is false. Okay, we already know an example of Euclidean geometry where all 5 of those postulates hold, right, by assumption. So then the problem is constructing a type of geometry where the first 4 hold and the 5th one doesn't. Okay, and so there are many equivalent statements. I've already mentioned one. So there's Playfair's axiom. So postulate 5, you know it's long form. The equivalent statements are, so here's one. This is Playfair's axiom, which is actually due to Proclus, apparently. So through, maybe I should write it like that, through a point not on a line, there is exactly one parallel line. So there's exactly one line parallel to it. Okay, this is probably the most commonly encountered version. For the others, I'm going to read them off here. So the next one is every segment is a side of a square with 4 right angles. This is due to Legendre. Not every pair of similar triangles is congruent. This is due to Wallace. Every triangle has a circumcircle. That's Legendre again. And there's at least one triangle whose angle sum is 180 degrees. That's again due to Legendre. So actually, yeah, we know in Euclidean geometry that every triangle has angle sum 180 degrees. And so actually it turns out that triangles having angle sum 180 degrees is a thing that is very closely tied to that 5th postulate. Okay. If you want to see a nice proof of this relationship, consider one of the classic proofs that a triangle has 180 degrees. The idea is to use some of these facts that you might recall from high school geometry, like alternate interior angles, right, formed by parallel lines being equal. That is also equivalent to the parallel postulate. Is it equivalent to it or is it implied by it? I have to think about that. But anyway, it's very closely related. I think it's actually equivalent to it. So if I draw a generic triangle, it's a bad triangle. So we'll say it has angle measures alpha, beta, and gamma. Okay, what's a classic way we can prove that these things sum to 180 degrees? The idea is I'm allowed to, using my straight edge, right? I can extend this line here. Okay, so I can extend this line segment there. It's extended. Okay, I can extend all these actually. Okay, so let's do that. Okay, I can extend all these. Now, I have a line. I have a point not on the line. It's this opposite vertex, right? Since this is actually a triangle, that is a point that's not on the line. Through that line, I can construct, through compass and straight edge, a line that is parallel to it. In fact, by this Playfair's axiom, right, there's exactly one of these, right? But there it is. Okay. Well, I know that alternate interior angles are congruent. That is, this angle and that angle are congruent, so those are both alpha. This angle and this angle are congruent, so those are both gamma. These 3 angles lie on a straight line, so their sum, alpha plus beta plus gamma, has to be 180. Because they're the sum of the angles on a straight angle, or on a straight line. Okay, so this is a classic proof of triangles having interior angle sum 180. You see how closely that is related to this question of drawing parallels through a point not on some line, right, to a given line. Okay, so anyway, going back, so here's a list of some equivalent things. These equivalent conditions were discovered by people trying to actually prove the for the most part, these equivalent conditions were discovered by people trying to prove the parallel postulate from the other four. As I said, it's not doable. Okay, it's impossible. But it wasn't known for a long time. Okay, so it turns out that that the parallel postulate is independent of postulates 1 through 4. And as the textbook notes, one of Euclid's enduring contributions to math is him implicitly basically assuming that this is the case because he includes the parallel postulate as an assumption. Okay, and the implication there is that it has to be assumed, because if you don't assume it, then it's not necessarily true. Okay, now Euclid didn't know of an example that would show that you could have a geometry that satisfied the first four postulates but not the fifth, because this wasn't known until 1829. Okay, so this geometry satisfying postulates 1 through 4 but not the parallel postulate wasn't discovered until 1829. Okay, so this is more than 2,000 years after Euclid. And so this was due to two mathematicians independently. One was Hungarian. His name was János Bolyai. So he did this, and essentially an equivalent result was obtained by Nikolai Lobachevsky. It is possible that Gauss actually knew this before these results, but it was not published. He was certainly close to figuring out these things, and Gauss was the one who proved the Theorema Egregium, which I'll mention later. Well, I can go ahead and mention it now. So I mentioned last time that another thing that spherical geometry had going against it, right? I have a sphere, okay, but the sphere sits in space, okay, and so as an example, the sphere was considered. If you hear my cat meowing, it's because he thinks I'm about to play with him because I got this toy. So the sphere sits in space. The thing about that, though, is that at the time, questions about geometry were asked in the following way: because it sits in space, it must inherit any geometric structure I'm talking about on this sphere. It must be inherited from how it sits in space. But I could also think about the inherent geometry on the surface, right? And so to talk about these maybe two different types of geometry that I might be discussing, I would talk about intrinsic quantities, so intrinsic geometry, that is geometry of the surface, not caring about the space that it sits inside, and extrinsic geometry, which is any geometric entanglement that might result from how it sits in space, okay? Now, there was a reason to believe that those two things were different, right? So it depended on how it sat in space. It turns out that those two things are the same. It turns out there's no such thing as intrinsic or extrinsic geometry. If you're careful, it doesn't actually matter how it sits in space. And so what that means is that you can throw away the ambient space. You don't have to think about it. So you could consider a space just in its own right, like nothing else exists. And so thinking about that, now the sphere becomes kind of a more proper model of a type of geometry, and it doesn't seem as exotic, or it doesn't seem like it is, sitting inside Euclidean space because I don't even have to think about the space it sits inside. Okay. Do concepts from linear algebra apply to non-Euclidean geometry? Yes. So, well, I should say that in order to nicely define non-Euclidean geometry, kind of the simplest model is something called the upper half-plane model. If you want to see an example of this, so I believe, let me look really quickly, I had them pulled up earlier. Let me make sure what videos these are, and I'll type them into chat. Well, it looks like I closed them out. I believe it is lecture 34 and 35, but let me make sure. Let me go to my channel and look at my videos. Let's see here. I look at my videos, Math 430. Yeah, lecture 34 and 35. So it starts halfway through 34. So I'll type that into chat. So for a model of hyperbolic geometry, which is what this is called, look at Math 430, lectures 34 and 35. It starts halfway through 34 and goes through 35 and on. For really the rest of the videos cover this model, but that's where the meat of it is defined. This is the easiest way to define it. It's called the upper half plane model. And so let me give a quick characterization here. So basically, consider this as the plane, but here's the x-axis. Here's the x-axis in the plane. Okay. Now I have it as a dashed line. This is the x-axis. Here's the y-axis. I have it as a dashed line because it's not included. So this is the upper half plane. The points on the x-axis aren't included. Okay. And so what is the length? Now I'm not going to get into exactly how this is defined, but I'll just give you a couple of examples. If I have a segment, okay, here, right? Now you might call that a line segment, but in this geometry, so this is a model, this is the upper half plane model. So this is the upper half plane model of hyperbolic geometry. Okay, so in the upper half plane model of hyperbolic geometry, I have an upper half plane. This looks like a line segment, but in this geometry, this is not a line segment. Okay, it just looks like one. But if I draw this thing and I wanted to compute the length of it, I'm not going to actually write out what the length of it would be, but I'm going to tell you that this length and maybe say that length are the same. Okay, how could that make sense? The easiest way to think about it is it's like I'm scaling this length by its height. And so as I'm closer to this x-axis can be thought of as at infinity. So it's infinitely far away. As I'm going down the y-axis, this is infinitely far away. The x-axis is some horizon. It's some thing that I'm never going to get to. And as I get closer and closer to the x-axis, this distortion is more extreme. So a tiny little length like this would be as long as this thing that I've drawn here. What do the lines look like, okay, in hyperbolic geometry, in this upper half plane model? The lines are either vertical lines, so that's a line in hyperbolic geometry. They're vertical lines like this. So this line continues indefinitely because, of course, it never reaches the x-axis here, and it goes off indefinitely in the positive y direction as well. So vertical lines. What's another type of line? Another type of line is a semicircle that has its center on the x-axis. So there's a line. Okay, a line segment would be a piece of these things. So it would be a vertical piece, or it would be an arc of a semicircle centered on the x-axis. So here's a line, and again, these have no ends, right? This line continues indefinitely because this is not included. Okay, and now you see how this fails the parallel postulate, right? Okay, so I'm going to draw a fresh picture here. So here's a fresh picture. I drew this as a solid line, but consider that this is the x-axis, so it's a dashed line. Here's the y-axis. Okay, so I'm going to draw a line. There's a line. Okay, given line. I'm going to draw a point not on the line. So let's see if this satisfies Playfair's axiom. Playfair's axiom, you know, that is the version of the Euclidean fifth postulate that says that through a point like this, not on a line, there is exactly one line I can draw that is parallel to the original line. Well, here's one. Okay, that is, it's parallel to it because they don't intersect. But here's another one. Here's another one. Here's another one. There's infinitely many. Right? So there are infinitely many parallel lines through this point, right, to my original line. Okay. So that's how this model works. If you want to see the specifics of how this works and why we're allowed to call these lines, even though they don't look like lines, right? You have to consider what does it mean for a line to be a line, right? So if you want to see that, look at the videos that I linked in chat, which are, well, I didn't link them directly. You'll have to look them up. They're on this channel. Math 430, lectures 34 and 35, starts halfway through 34. This begins the discussion of the upper half-plane model hyperbolic geometry. So it actually wasn't even until 1868 that a mathematician by the name of Beltrami came along and gave a model that actually showed that this was an honest-to-God different geometry. There was no way to reconcile this with Euclidean geometry, so it was truly non-Euclidean geometry. So Beltrami did important work here. There's what's called the Beltrami-Klein model. That is not this, though. So Beltrami-Klein model is not the upper half-plane model. There's the Poincaré disk model by Henri Poincaré, which is another very beautiful model of hyperbolic geometry. There's a number of models. This is kind of the easiest one to understand and to define, but there are other models that require a little bit more advanced mathematics that are equally fine for giving more models of hyperbolic geometry. And this was the first thing that showed that, oh, well, it's not that the Euclidean axioms. You might say, like, what's the big deal, right? So there's a different type of geometry other than Euclidean geometry. The reason why this is a big deal is because up until now, like up until this time, right, in the 1800s, Euclidean geometry wasn't viewed as just being some, like, special rule set that people did math in. It was viewed as being, like, the fundamental truth of the universe, right? It was viewed as, like Euclidean geometry was the setting that computations were done in, you know, like Newtonian mechanics, right? So if you wanted to compute something, right, the motion of heavenly bodies or something like that, the computations done assumed, you know, a Euclidean space that you were doing them in. So it was viewed that we were living in this Euclidean universe, basically. And so these axioms weren't just convenient things that had been assumed and weren't actually true. These axioms were like self-evident truths of the universe. And so the fact that you know, one of these axioms, one of these postulates was actually false, you know, it could be shown that you could construct a model that, you know, that didn't satisfy it. That is, you could talk about a geometry with a different list of assumptions, right, and it was totally logically consistent. What that meant is that, and Poincaré probably said it best, where he said, Euclidean geometry is no more true than hyperbolic geometry or elliptic geometry or any other kind of geometry. Basically, a geometry cannot be more true than another type of geometry. It can only be more convenient. That's what Poincaré said. And the idea here being that, well, like, you can play with the list of assumptions. And if you play with the list of assumptions, you can get different types of geometries, as we see. This was a big deal because at the time, like I said, Euclidean geometry was seen as being part of the fundamental truths of the universe. So it's not really something you could mess around with the assumptions on, because you didn't have a choice in the matter, right? These axioms were found by looking around, observing, and saying this is how things work. So it's not like there was a choice involved, but it turns out there was. And in fact, what's amazing is that mathematicians had worked all of this out, almost 70 years prior to Einstein's relativity, right? Which, by that time, and Einstein wasn't the first to do work on this. In fact, Poincaré himself, right, was actually the first to publish a paper on relativity. He was the first person to write out E equals mc squared. Lorentz, before Einstein, had also done similar work. Minkowski had done similar work. So this was, this all culminated in what laid the basis for relativity now, which of course says that the universe is non-Euclidean, right? So the universe we live in is non-Euclidean. So we thought we lived in a Euclidean universe, and the reason that that's the case now, if we're being Pythagoreans, is that we live on an object that is locally Euclidean, right? Or we live in a region of the universe that locally looks Euclidean. So locally, you look around and things look flat, okay, which is a characterization of being Euclidean. But as you zoom out, right, the universe is not just flat. And so it is apparently non-Euclidean, right? And so that's more or less, the big paradigm shift there, where what was taken as fundamental truth of the universe turned out to not be fundamental truth of the universe. It turned out that this notion that you can change the assumptions in this way to get another type of, what might have been viewed, and at the time was kind of viewed as a silly novelty, right? The notion other types of geometry, that's ridiculous, right? It might be interesting to investigate, but it has, of course, clearly no application, right? Well, of course, it turns out that, the universe we live in is non-Euclidean. And so, if anything, Euclidean geometry is less applicable than the non-Euclidean geometry that followed. And so I'll talk more about that as we get closer to the 1800s, and I discuss Gauss and Riemann and other things like that. I wanted to mention that in 1899, David Hilbert, great mathematician, decided to take it upon himself to see what was necessary in order to make Euclid 100% logically sound in everything that followed in the Elements. And it turns out that it didn't take a whole lot. The only thing that you needed to carry out Euclidean geometry in a way that is 100% rigorous, according to modern standards, is a list of axioms. I believe there's 21 of them, 19, 21. How many total? I think it's 19 axioms, yeah. So anyway, these are called Hilbert's axioms. Okay, and so these axioms are meant to replace the postulates of Euclid. But notice, so just to give you an idea, there's too many of them to go through line by line. Just to give you an idea, some of the things they say. So here, let me bring it a little bit closer. So these are the incidence axioms. So this has to do with conditions for points to lie on lines or for lines to pass through points. So the intent, right, was if I want to be able to rigorously talk about, say, even proposition 1 in the Elements, which requires that I have two circles and they intersect. I have to have some notion of incidence, of things intersecting. So first incidence axiom, for any 2 points AB, a unique line passes through AB. Okay, so that's 2 points to determine a line. That's actually that was actually one of Euclid's original postulates. Incidence axiom 2, every line contains at least 2 points. This is to guarantee a sort of, this is a minimality condition, okay? That I can't remember exactly where this technically becomes a problem, but maybe even in Prop 1. There exist 3 points, not all on the same line. Okay, so again, this is a minimum size of the space in question, right? Okay. Here's incidence axiom 4. For each line L and point P not on L, there is a unique line through P meeting L, this is the parallel axiom or the parallel postulate. So incidence axiom 4 is the same as Euclid's fifth postulate. Now all of these, there's a whole list. So there's betweenness or order axioms that basically addresses the fact that you need some kind of ordering, and you need a notion of betweenness, of points being between other points, which requires a type of ordering on a set. There's also statements about congruence and congruence of line segments and congruence of angles. So there's a bunch of those axioms. Here's a very important axiom that's included that is labeled D because it's called a Dedekind axiom. You've seen that name before, right? Compared with Eudoxus. This is the completeness axiom. This is the thing that you need. If you don't do anything, if you don't include this, okay, everything in Euclid's Elements, like absolutely everything in Euclid's Elements can be done with all of the axioms Hilbert includes, even without this one. The only reason you need this one is so that the plane that you construct is exactly R2, the plane of ordered pairs of real numbers. Without this completeness axiom, you get the constructible plane. Okay, so the only coordinates that you could construct, or the only coordinates that you could get in this plane would be the ones you can construct with compass and straight edge. So the ones that you can get from the rational operations together with extracting square roots, right? That's what you get. But with this, you get everything. You get pi, you get cubed roots of 2, you get everything. Okay. So Hilbert's axioms, the importance of them is not that they're necessarily convenient. They're a long list, right? Much longer than 5 axioms and a few common notions. So much longer than Euclid's list. But one, they're important because they show that this program that Euclid tried to do can really be done. Okay, it can be done to a level of rigor that is, our current, standard for what it means to be a rigorous proof. So basically, Euclid's approach can be totally completed in this way. Okay. Now, so I have a couple minutes left, and so I wanted to start a discussion on Alexandrian mathematics up until 200. So I'll at least get the names down, and then Friday I'll finish this and hopefully talk about Archimedes. I'll have to change the description of this video a little bit because I thought I might get a little bit further. And so Alexandrian mathematics. From roughly 300 BC to 200 AD, or sorry, not 200 AD. We'll be skipping there in a little bit, but from 300 BC to 200 BC. So there are a few names that pop up. These were students of the Alexandrian school. Archimedes, I'm not exactly sure what evidence exists to suggest that Archimedes definitely studied in Alexandria, but that's an assumption from history. I'd have to actually look at the sources to see what led people to believe that. I know that some of the letters supposedly ascribed to Archimedes were addressed to Alexandrian mathematicians, so it's not out of the realm of possibility. So a few. There's Aristarchus. So Aristarchus lived from 310 to 250 BC. Okay, so we'll talk about him next time. There's Archimedes of Syracuse, studied in Alexandria supposedly, but was known, most of his productive life was spent in Syracuse. There's far too much to say here. From 287 to 212 BC, he died in the siege of Syracuse. I'll talk more about that when I talk about Archimedes, because I have a ton to say there, because he died during the Second Punic War, which is my favorite time in history. In all of history, the Second Punic War is like my absolute favorite little window of history. There's Apollonius of Perga. So he lived from 260 to 190 BC. As we'll see next time, I actually, check it out, my book that I've been referring to, right, that has Euclid's Elements. Look, see if you can see that. It's a little too much glare there. Let's see if I can focus it. Look what it says. Euclid, that's Euclid's Elements. It has a few papers by Archimedes, okay, more than one. And look who's next, Apollonius of Perga. right? Who's exactly this guy that I want to talk about. It also includes Nicomachus, but these three are the big ones. And so, let's see. Let me zoom back in. And so Apollonius of Perga is important. The textbook actually doesn't pay him much mind, so I'm going to talk about him more than the textbook does because he's actually pretty awesome. He is responsible for bringing conic sections up to like the modern standard. So Apollonius of Perga, what he did with conic sections was something that was unsurpassed until the 1600s, till calculus. Okay. So it was actually pretty impressive. And then Eratosthenes. So Eratosthenes, you have already heard. So Eratosthenes of Cyrene, who lived from 275 BC to 195 BC. So Eratosthenes, you've already heard his name. That was it was attached to the sieve of Eratosthenes, which was this method of finding prime numbers, right? This really crude method of listing out numbers and then being able to follow this algorithm that, I was able to circle numbers and then cross out all multiples, and then the numbers that I circle after I do this process, I've generated a bunch of prime numbers. So sieve of Eratosthenes is due to him. He also, the thing that he's most famous for is not necessarily a mathematical achievement. Well, I shouldn't say that. I mean, it's a thing that gets brought up a lot in history of science classes, which is he computed the circumference of the Earth to an amazing accuracy. And I'll talk about the method that he used to do that because it's pretty ingenious. And all it involves is really, really basic geometry. So Eratosthenes had really, really good idea when it came to that. I believe he's also the one responsible for estimating the axial tilt of the Earth. And he was also really, really close to that. I believe he literally said, like 23 degrees. That was the axial tilt of the Earth. So he's really, really close. So anyway, Eratosthenes was well known for those two things, in addition to the thing you've already heard his name in connection with. So anyway, I will finish these next time. Archimedes will get his own section, so we won't talk about him first. We will talk about Aristarchus, Apollonius, and Eratosthenes, and then I'll talk about Archimedes on his own, because even devoting like an entire lecture to Archimedes would not be nearly enough. But that is basically all I'm going to do because we don't have time to go into too much detail, but I can give more detail about that. But Archimedes was truly was truly amazing. Anyway, I believe that's it for today. So I will see you all on Friday, where we start here. And by the end of Friday, maybe by the end of next Monday, we will be almost to the beginning of the Dark Ages. Okay, we'll be almost to the official end of Greek mathematics and the beginning of the Dark Ages. So anyway, I will see you all Friday.